Alright, welcome back. This is the Tutor Wizard. I'm Adrian. This is Willa. We're going to do some math. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and many other ones on our channel. Isn't that right? This time we're doing multivariable calculus. We're in chapter 1. We're going to do finally section 1.4, tangent planes. There's going to be a lot of sections in this chapter and all the chapters. I like multivariable calculus. This lecture, what we're going to do is the equation of a tangent plane for functions of two variables, and then we'll do a couple examples. Let's get at it, right? Alright, so what is the tangent plane? Again, let's first start with the geometric avatars of what's going on, and that gives a whole much more intuitive, for lack of a better word, way of looking at this before we get all of the horrible algebra. And this is where we're definitely now going to mesh a bunch more linear algebra terminology with calculus, because now we're talking about a tangent plane, and the best way to describe planes, lines and planes in three spaces in linear algebra when we have the normal equation and the vector equation. So we're going to remind ourselves of that quickly in a second. Linear algebra, here it comes. What are we doing? First of all, when we did partial derivatives in the previous videos, also in the last section 1.3, when we give the definition in particular of partial derivatives, we set y naught to be constant, and then we get a plane y equals y naught. I didn't draw it in here, but it will intersect this way, and it will intersect my curve in the red curve. I didn't draw them in. I'm a bad boy. That's the only thing I forgot in the picture. What was missing? Gamma 1. The curve of intersection of y equals y naught and my surface S. And then I have also gamma 2. Now, what I have with that scenario is I have two tangent lines, T1 to gamma 1 and T2 to gamma 2. The tangent plane to surface S, the easiest way to do that without any mumbo jumbo, the actual definition of what we're meaning pictorially, and then you go into higher dimensions, the hyperplane or hypersurface tangent to the surface at that point will be the tangent surface, hypersurface containing all of the tangent lines. I don't know where the fourth direction is. Not in any of these directions. For us, a tangent plane to a surface, or which is the graph of a function of two variables, is the tangent plane containing both of these tangent lines, T1 and T2. Now let's get an analytic specific expression for that involving the partial derivatives of f with respect to x and y. Bye. Now we just looked at a fancier picture of this. I've got stripped away all the stuff that we need now. Here's the surface, which is the graph of the function of two variables, which is when now we're at a point x naught, y naught, f of x naught, y naught. And we want to discuss the tangent plane to my surface S at this point. What that is that plane is the plane in 3 space which contains this tangent line and this tangent line. The tangent lines which are the tangent to the curves which intersect those guys, yada yada yada. Now we want the equation of that specifically from linear algebra. See my previous videos, I have a linear algebra playlist. We describe specifically how to find the most efficient form of equations of lines and planes in 3 space. In particular, we have the normal equation of a plane, and if we have the normal vector a, b, c to that plane, and we have vector r minus r naught in that plane, the normal equation is the normal vector dot product with that vector laying in my plane. Their dot product should be equal to 0, and I can create this equation, linear algebra. From that, now I want to simplify specifically, and now we're kind of trying to view this as an equation z equals something, because we are now talking about functions of two variables. So the first thing we do is we're solving for z in this equation is what they're doing. So I make the move by dividing by c. I'm assuming c is not 0. By doing that, I get these two numbers, I call them, and I'm going to get this equation like this. Then what I want, then this is the equation of the plane that we're looking for every time. So when they say do this and we do an example right away, this is what they're looking for. What's left? Done. No. We're not done. What do I have left? I need these two guys. I want to know what m is and what n is. That shouldn't take us too much if we cleverly think about this for a second, though. Now, what we're going to do is set y equal y naught. temporarily. That kills this. And then what's left? I have an equation, z equals mx plus something plus a number. So this is an equation of a line, which is the equation of the tangent line of z in the direction of x. So who is m? M is the derivative, which is in this case the partial derivative of f with respect to x. If I now do the same thing and I don't do this and I set x equal to x naught and I hold this constant, then this term will go away and I get another equation of z with respect to a linear equation of z with respect to y. That's the tangent line T2 to my equation. And so what's his slope? His slope is going to be fy, or the partial derivative of f with respect to y. So now I know explicitly what those guys are going to be without analytically proving it for you. Who are those guys going to be? Let's write out that equation out. It's going to be, this is T1 and T2. So z minus z naught. Remember who z naught is. This is fx, x naught, y naught, which looks horrible, but he's a number. The slope of the tangent with respect to x of our function times x minus x naught, m, plus n, which is now the partial derivative of f with respect to y at the point x naught, y naught, times y minus y naught. This is our plane. And who is z? F of x naught, y naught. Let's do an example. All right, so we're going to do, here's the equation of the tangent plane one more time. Waiting for my cameraman, sorry, I was flipping the marker. That was only 2. I can do 3. When you're in the stadium, like COVID, when there's no COVID, I can do it like 4 or 5 because you can throw away up. I can't even count. Rotations, we'll do those later maybe. We have the equation of the tangent plane. Let's discuss that one more time quickly. This is the first partial derivative of f with respect to x now, which was the slope of the tangent when we did this, when we held y constant. Now we have the first partial derivative, but this is going to be a number also. And then this is z, so we get a point x naught, y naught in our domain of our function. Then z is f of x naught, y naught, and that's z minus z naught. So that's where he came from. I bring him to the other side. In one dimension, we get the tangent line, not the tangent plane, is equal to f prime of a, x minus a, plus f of a. Now we have 2 of the terms, not just 1. This is the derivative in the direction of x plus f at a. Now I have the derivative of x in the direction of x minus x naught, the derivative of f with respect to y minus y naught, plus z, which is f of x naught, y naught. When we do a function of 3 variables, guess how many terms there's going to be? Oh, there's going to be a z minus z naught, and a partial derivative of f with respect to z, and then a w of x naught, y naught, z naught, and then when we go more dimensions, more terms. Let's do an example. And where'd you go? All of this seems so scary. I claim I can do the solution in this space. So not so bad if you know what you're doing. What do I need to do this? This guy, this guy, this guy, and these guys. Stir them in the pot. All right, I need the partial derivative of f with respect to x. This is f. What is that going to be? E to the x minus y times 1 by the chain rule. If I do fy, what am I going to get? Negative e to the x minus y. Again by the chain rule. Now this time, don't forget. Now what do I need? I need fx at 3, 3. This is x naught, y naught, z naught, which is f of x naught, y naught. We already gave it to me. It's a 1. So this is equal to what? Fxx at, this is e to the 3 minus 3, which is 1, e to the 0. Fy is negative e to the 3 minus 3, which is negative 1. I've got these numbers now. I've got this number now. We're done. the tangent plane is Z is this hot mess. 1, x minus 3, my point, plus this hot mess, negative 1, y minus 3, plus, oh, what is it? Plus 1. This is the equation of the tangent plane. Let's do one more. Good. I probably could have erased that. We might not need it anymore, but there it is every time. This is what I tried to memorize and picture in my head, and then when you go into an exam, we see this. What am I filling in? I have to fill in the two blue guys, and that guy which they gave us. This is x naught, this is y naught, this is f of x naught, so I've got those guys. That's 0, and that's 0. I've already got those three. They gave it to me. Then what do I need? These two guys evaluated at 0, 0, x naught, y naught. So I need the first partial derivative with respect to x and y, and then I have to put them 0, 0, and then we build our equation of our tangent plane. Can we do it in a space? Otherwise, unless I get the partial derivatives are a hot mess, maybe not, but let's see. Fx, or switch to Leibniz, the partial of z with respect to x. Know your terminology, that means the same thing. Fx, that is cos y minus y e to the x. And the partial of z with respect to y, practice doing those, it takes a while, equals now negative x sine y minus e to the x. I should have stuck those in there, but can I get that? What is, now I switched the notation for convenience. I ran out of room, so now back to that. That's the same guy. This guy. That is fx at 0, 0. That gives me what? Y of 0 is 1 minus 0 times 1 e to the 0. So that gives me 1. And fy of 0, 0 is equal to sine of y is 0. And then minus, oh look, we got, I didn't even try, I just stole this out of a book, but look, we got the same slopes in both of them again. Coincidental, this guy has the same ones, but he's through the origin this time, the last one wasn't. What are we going to get from this? The equation of our tangent plane is z equals the first partial evaluated at 0, 0, 1 times x minus 0 plus negative 1 times y minus 0 plus 0. Our plane is z equals x minus y, or bring them all to one side, x minus y minus z equals 0. This is the equation of the tangent plane. That looks more like linear algebra. Leave it like this if you want. Final answer. Don't waste any time. Please subscribe right here. Hit the notification bell. You'll get notifications for how to do tangent planes or do anything in math. I'm the Tutor Wizard. See you next time.